I'm focusing on how to make Birch clustering faster when dealing with tons of data. We're talking millions of data points here. That's a big job for any algorithm. This highlights the scale of the problem. Millions of data points means standard clustering techniques will take forever. That's why we need smart strategies to speed up the Birch algorithm. Birch builds a special tree-like structure called a carbon monofluoride tree, clustering feature tree, to organize data points efficiently. This tree is crucial for the algorithm's speed. Optimizing its construction is key to solving the problem. After the carbon monofluoride tree is built, Birch uses a method similar to k-means to assign the data points to the final clusters. But this step is less important for optimizing the entire process. Increasing this value makes the carbon monofluoride tree wider and shallower. This speeds up tree building. Think of it like building a wider, shorter pyramid. It's faster than building a tall, narrow one. This only affects the final k-means-like step. It doesn't change how quickly the carbon monofluoride tree is built. So, changing this doesn't help us speed up the initial tree construction. A smaller threshold makes the algorithm create more, smaller clusters. This makes the carbon monofluoride tree much more complex, slowing down the whole process. Using a smaller sample for the initial tree construction means building the carbon monofluoride tree on a smaller dataset. It's like building a small model first, then refining it. This dramatically reduces initial computation time. I'm focusing on how to make the Birch clustering algorithm run faster, especially with massive datasets. We're looking at how to tweak settings to improve efficiency. The core question asks us to identify the parameter adjustments that speed up Birch clustering. I'll use a smaller initial subset of the data to build the initial tree structure. This significantly cuts down on the initial computation time. Think of it like making a small sketch before painting a mural. It's much faster to get a basic idea that way. Lowering this setting means points have to be closer together to be grouped. This leads to many tiny clusters and a much more complex tree, making the process slower. It's like trying to sort many small, similar objects. It takes longer. I see that optimization involves finding the best balance between speed and accuracy. Let's find that sweet spot. Changing the number of final clusters only affects the last phase, after the main tree is built. It doesn't impact how fast the tree is constructed. It's like deciding how many final colors you want in your mural after the initial sketch is complete. It doesn't change how long it took to make that initial sketch. A higher value creates a wider, shallower tree. This means less searching is needed when building the tree, leading to faster construction. Imagine a shorter, wider tree instead of a tall, narrow one. You can climb it faster. I've got it. The best strategies to boost the Birch algorithm's efficiency are those that improve the tree building speed, without sacrificing too much accuracy. Let's get clustering. I found that increasing the branching factor speeds up the Birch algorithm. A higher branching factor creates a wider, shallower tree, meaning less traversal time during tree construction. Think of it like building a wider, shorter pyramid instead of a tall, narrow one. Building the wider pyramid is faster. Also, using a smaller sample size to build the initial tree significantly cuts down on initial computation time. This is like working with a smaller, more manageable subset of your data first. You'll have a faster initial calculation. I discovered that decreasing the threshold makes things slower. A smaller threshold forces the creation of many small clusters, leading to a far more complex and time-consuming carbon monofluoride tree to build. Imagine trying to sort many tiny pebbles versus a few large rocks. The pebbles will take significantly more time. I learned that changing the number of clusters, n_clusters, only impacts the final clustering step, not the carbon monofluoride tree building process. This happens after the tree is already built, so changing it won't directly speed up or slow down building the tree itself. It's like changing the final arrangement of the sorted pebbles. It doesn't change how long it took to sort them. I see branching factor as the maximum number of children each node in the carbon monofluoride tree can have. A higher branching factor makes a wider, shallower tree, which often speeds up tree building. Think of it like a wider highway. More lanes mean less traffic jam. Sample size is how many data points I initially used to build the tree. A smaller sample size means less initial calculation. It's like building a smaller model before building a larger one. It might not be perfect, but it speeds up the early stages. The threshold determines how close data points need to be to join the same cluster. A smaller threshold means many small clusters, making the tree complex. A larger threshold means fewer, bigger clusters, making the tree simpler and faster to build. Think of it as a magnet's strength. A weaker magnet, smaller threshold, attracts only nearby points, while a stronger one, larger threshold, pulls more widely spread points together. The n_clusters parameter determines the final number of clusters I want. It only comes into play after the tree is built, so it doesn't directly affect how fast the tree is built. It's like deciding how many final rooms I want in my finished house. That doesn't affect how long it takes to build the frame. I'll explain why using a smaller sample size is a good idea for speeding up birch clustering. Think of it like this. You're trying to build a map of a huge city. Instead of surveying every single house, you could first survey a smaller, representative sample. This initial overview gives you a good starting point for building the complete map, and it's much faster. A smaller sample size lets the algorithm build a preliminary carbon monofluoride tree quickly using just a subset of the data. This significantly reduces the initial computation time, even though the final result might not be perfectly precise. Let's talk about the branching factor. Imagine a tree. A higher branching factor means each branch of the carbon monofluoride tree can have more children nodes. This results in a wider, shallower tree. It's like having more lanes on a highway. More lanes mean less congestion, and building this wider, shallower tree is faster. Therefore, increasing the branching factor speeds up the tree building process. The number of clusters you want at the end is completely separate from the time it takes to build the carbon monofluoride tree. Think of building a road network and deciding how many towns you want to connect later. The number of towns doesn't influence how long it takes to build the roads themselves. Increasing the desired number of clusters, n_clusters, only affects the final clustering step, not the tree building phase, which is what we're trying to speed up. I'll explain why decreasing the threshold is bad for performance. A smaller threshold means you're requiring data points to be extremely close to belong to the same cluster. This results in many more tiny clusters and makes the carbon monofluoride tree much more complex and time-consuming to build. Think of trying to sort thousands of tiny pebbles instead of large rocks. It's much more effort, and takes longer. This is the title, highlighting the core topic. How to make birch clustering, a method for grouping large datasets, run faster. We'll explore ways to tweak Birch's settings to achieve that. I see, using a smaller sample of the data to build the initial tree structure makes the process much quicker. Imagine building a small model of a building before tackling the full-scale project, much faster and easier. This speeds up the initial phase significantly, and it's a great optimization strategy for huge datasets. Here's the deal. A more intricate tree leads to a slower build. Just like a sprawling, complex city takes longer to build than a small town, this approach significantly impacts building time. Therefore, we should try to keep the tree structure simple and efficient for faster processing. Let's talk about the carbon monofluoride tree, which is like a map that organizes the data points. A wider, shallower tree is easier and quicker to build than a narrow, deep one. Just like it is faster to traverse across a wide, short river than a narrow, deep one. This speeds up the entire clustering process.